Understanding the water cycle is important in order to understand hydropower. The energy driving the water cycle comes from radiant energy released by the sun that heats the water and causes it to evaporate. In addition to the water cycle, hydropower is dependent upon stored gravitational energy. A rock on top of a hill contains potential energy because of its position. If a force pushes the rock, it rolls down the hill because of the force of gravity. Potential energy is then converted to kinetic energy until it reaches the bottom of the hill and stops. Humans have used the power of moving water for more than 2,000 years. The first references to watermills are found in Greek, Roman, and Chinese texts. They described vertical water wheels in rivers and streams. These traditional water wheels turned as the river flowed, turning millstones that ground grains. In the late 1700s, an American named Oliver Evans designed a mill that combined gears, shafts and conveyors. After grain was ground, it could be transported around the mill. The invention led to water wheels being the main power source for sawmills, textile mills and forges through the 19th century. In 1826, a French engineer, Jean-Victor Poncelet, designed an even more efficient water wheel. The wheel was enclosed so the water flowed through the wheel instead of around it. In 1880, the Grand Rapids Electric Light and Power Company used a water turbine to generate enough electricity to power 16 lights. Soon after, in 1882, the world's first hydroelectric power plant began operation on the Fox River in Appleton, Wisconsin. The plant, later named the Appleton Edison Light Company, was initiated by Appleton paper manufacturer H. F. Rogers, who had been inspired by Thomas Edison's plans for an electricity producing station in New York. When you look at rushing waterfalls and rivers, you may not immediately think of electricity, but hydroelectric power plants are responsible for lighting many of our homes and neighborhoods. Over one-half of the total U.S. hydroelectric capacity for electricity generated is concentrated in a few states in the western United States: Washington, California, and Oregon. Washington is home to the location of the nation's largest hydroelectric facility, the Grand Coulee Dam. It is important to note that only a small percentage of all dams in the U.S. produce electricity. Most dams were constructed solely to provide irrigation and flood control. Over one-half of the total U.S. hydroelectric capacity for electricity generated is concentrated in a few states in the western United States: Washington, California, and Oregon. Washington is home to the location of the nation's largest hydroelectric facility, the Grand Coulee Dam. It is important to note that only a small percentage of all dams in the U.S. produce electricity. Most dams were constructed solely to provide irrigation and flood control. South America produces a little more than half of electricity using hydropower, 53%. Most electricity from water in U.S. and the world is produced by conventional hydropower using gravitational energy. Almost 17% of the world's electricity and 5 to 10% of U.S. electricity, depending on the supply of water, is produced by hydropower. That's enough power to supply 28 million households with electricity, or the equivalent of nearly 500 million barrels of oil. The total U.S. hydropower capacity is about 95,000 megawatts. So just how do we get electricity from water? Controlled flowing water is the power source used to turn a propeller-like piece called a turbine. The turbine then turns a metal shaft in an electric generator, which is the device that produces electricity. The idea is to build a dam on a large river that has a large drop in elevation. There are not many hydroelectric plants in Kansas or Florida where rivers travel on flat land. The dam stores lots of water behind it in the reservoir. Near the bottom of the dam wall there is a water intake. Gravity causes it to fall through the penstock inside the dam. At the end of the penstock there is a turbine propeller, which is turned by the moving water. The shaft from the turbine goes up into the generator, which produces the power. Power lines are connected to the generator that carry electricity to your home and mine. The water continues past the propeller through the tail race into the river past the dam and exits with great force. In a hydropower plant, a hydraulic turbine converts the energy of flowing water into mechanical energy. A hydroelectric generator converts this mechanical energy into electricity. The operation of a generator is based on the principles discovered by Faraday. He found that when a magnet is moved past a conductor, in this case, coils of copper wire, it causes electricity to flow through the wire. In a hydropower plant, a hydraulic turbine converts the energy of flowing water into mechanical energy. A hydroelectric generator converts this mechanical energy into electricity. The operation of a generator is based on the principles discovered by Faraday. He found that when a magnet is moved past a conductor, in this case, coils of copper wire, it causes electricity to flow through the wire. In a large generator, electromagnets are made by circulating direct electrical current through loops of wire wound around stacks of magnetic steel laminations. These are called field poles, and are mounted on the perimeter of the rotor. The rotor is attached to the turbine shaft, and rotates at a fixed speed. When the rotor turns, it causes the field poles, the electromagnets, to move past the conductors mounted in the stator, or the wall. This, in turn, causes electricity to flow and a voltage to develop at the generator output terminals. Rotational speed. The rotational speed of the generator is usually the same as the speed of the turbine, because they are directly connected. Some plant designs incorporate a speed-increasing gearbox between the turbine and generator. The speed of the turbine is determined by the design and hydraulic conditions. Speeds for hydro generators are typically in the range of 50 and 600 revolutions per minute (RPM). For a generator operating in a 60 Hz system, the rotational speed in RPM times the number of field poles on the rotor is always 7,200. The stator is a donut-shaped structure surrounding the rotor. The stator is made up of a steel frame supporting stacked steel laminations. The conductors, called the stator winding, are recessed in slots in this lamination structure. The stator winding is arranged so that when the rotor turns, the field poles pass only a fraction of an inch from it. The movement of the magnet next to the conductor causes electricity to flow in the conductor. Stator windings of larger generators are made up of individual stator coils. Each coil is made of multiple strands of copper. In a modern insulation system, the copper is insulated with mica held in place with an epoxy or polyester resin. The individual coils are connected to each other through jumpers and then to a ring bus. The ring bus is connected to the generator leads, which in turn are connected to a power step-up transformer. Finally, the transformer is connected to electrical power grid. Some generator designs use half coils bars in lieu of full coils. Hydropower is fueled by water, so it's a clean fuel source. Hydropower doesn't pollute the air like power plants that burn fossil fuels, such as coal or natural gas. Hydropower is a domestic source of energy, produced in the United States. Hydropower relies on the water cycle, which is driven by the sun, thus it's a renewable power source. Another advantage is the high efficiency of hydroelectric power plants. Efficiency of a power plant is determined by calculating the amount of energy going into a power plant compared to the amount of useful energy generated by the plant. In the case of most thermal power plants, for every 100 units of energy coal, natural gas, etc. that go into that plant, only 35 units of electricity are produced. This means they are only 35% efficient. 65 units are converted into other types of energy, mostly heat, which is dissipated into the atmosphere. A hydropower plant, on the other hand, converts about 95% of kinetic energy of the water flowing through the system into electricity. A hydropower plant produces no air pollution because it does not burn fuel, but hydro-powered electricity is not without its drawbacks and does affect the environment in other ways. Fish populations can be impacted if fish cannot migrate upstream past impoundment dams to spawning grounds, or if they cannot migrate downstream to the ocean. Upstream fish passage can be aided using fish ladders or elevators, or by trapping and hauling the fish upstream by truck. Downstream fish passage is aided by diverting fish from turbine intakes using screens or racks or even underwater lights and sounds, and by maintaining a minimum spill flow past the turbine. Hydropower can impact water quality and flow. Hydropower plants can cause low dissolved oxygen levels in the water, a problem that is harmful to riparian riverbank habitats and is addressed using various aeration techniques, which oxygenate the water. Maintaining minimum flows of water downstream of a hydropower installation is also critical for the survival of riparian habitats. In addition to the significant threat that dams pose to fish populations and the ecosystems of rivers and streams, hydropower can negatively impact both the flow and quality of water. Lower levels of oxygen in the water can present a threat to animal and plant life. However, these issues can be addressed if fish ladders are put in place to ensure safe passage around the area, and the water is aerated on a regular basis to maintain adequate oxygen levels safe for animal and plant life. The flow of water should be monitored closely to prevent the ecological dangers associated with overstressing bodies of water. These dangers can easily be avoided by shutting down pumping operations temporarily to allow balance to return to damaged ecosystems. Hydropower can be impacted by droughts. When water is not available, the hydropower plants can't produce electricity. New hydropower facilities impact the local environment and may compete with other uses for the land. Those alternative uses may be more highly valued than electricity generation. Humans, flora, and fauna may lose their natural habitat. Local cultures and historical sites may be impinged upon. Some older hydropower facilities may have historic value, so renovations of these facilities must also be sensitive to such preservation concerns and to impacts on plant and animal life.